Namaskar friends. Welcome to the educational video lecture series by MedDevice Circle. In this video lecture series, we are covering the fundamentals of clinical chemistry tests which are usually performed in pathology labs. This video lecture series is intended to be viewed by newcomers who have recently completed their education and who want to start their career in IVD industry, or experienced people who want to freshen up their knowledge of clinical chemistry test. This is also for our brothers and sisters who work in the field of lab technicians who want to understand the basics and fundamentals of clinical chemistry test. So without wasting any time, let me go back to my slides. And friends, this entire video lecture series is made in collaboration with Anamol Laboratories Private Limited. So allow me to share my screen. Friends, I hope you are able to see the screen. So as I previously mentioned, this entire video lecture series is to understand the fundamentals of clinical chemistry test that is usually performed in pathology labs all across India. So this entire video lecture series is divided into four different modules. In first module, we covered what are the basics of photometry, in which we understood what is wavelength, what are complementary colors, what is Beer-Lambert's law, and how do we use Beer-Lambert's law in our day-to-day life. We also understood what are the components of a colorimeter, and we understood what is the difference between colorimeter and spectrophotometer. In the second module, we discussed what are the role of enzymes in diagnostic test, in which we understood what are the generic role of enzymes, what are the factors that affect the enzyme kinetics or enzyme activity. We also understood what are the different types of biochemical reactions that happen in pathology lab. For example, endpoint reaction or kinetic reaction. We also understood that if you have the pack insert of any company, then how do you read the pack insert of that particular product? We also understood what are the common terminologies which are used in IVD industry in a pathology lab. All of these videos are available in our lecture series. So you can visit those lectures if you are interested to learn more about these topics. Today we are going to cover our third module. In this module, we are going to discuss a lot about quality control, QC in short. And I'm sure you must have heard this word a lot if you are in IVD industry. So in today's video, we are going to understand what is QC Sera and what are the uses of QC Sera in our day-to-day life. So without wasting any time, let's understand what is quality control and what is QC. So friends, we have understood in our previous video lecture series that if, say for example, if I make a weighing balance, if I manufacture a weighing balance and I stand on the weighing balance and the weighing balance shows me a weight of 500 kilos. We all know that my weight is not 500 kilos, but the weighing balance is showing me the weight of 500 kilos. So how do we understand that the weight which is given by the weighing balance, is it correct or is it not correct? Until and unless we do not have a known weight which we will use to calibrate the machine. In short, what I mean by calibrate the machine is that if I have a known weight of 1 kilo, I will put that weight on the weighing balance and I will teach the weighing balance that, hey, 1 kilo means this much heaviness. So machine will learn how much heavy is 1 kilo. And then after that, when I stand on the machine, then the machine will calculate my weight in comparison to the heaviness of what it is being taught previously. So if my heaviness is, for example, 50 times more than the weight of 1 kilo, then the machine will tell that my weight is 50 kg. So in short, we have one known value weight, which is very, very important to calculate an unknown weight. Similarly, in our IVD industry, especially in diagnostics, if we have to calculate any analyte concentration or the activity of enzyme, we cannot calculate the value of unknown sample until and unless we have an already known value sample along with that. So this known value sample is sometimes called as quality control sera. So QC Sera or quality control sera is nothing but it is a human serum for which the value of that particular analyte is already known to us. This is important for two primary reasons. Number one reason is the QC Sera is used to calculate the value of unknown sample. Hypothetically, if I want to calculate the value of glucose in a patient sample, then until and unless I do not have a known value, that means a sera or an artificial liquid in which the value of glucose is already known to me, until and unless I do not have that, then I will not be able to calculate the value of unknown sample. So quality control sera is used to calculate the value of unknown sample of any particular analyte. The second purpose of quality control sera in pathology lab is to check the dependability of the result. So hypothetically, if I run a glucose test for any patient sample, how will I come to know that I have performed the test correctly? So I will only come to know that I have run the test perfectly by also running a quality control sera along with the patient sample. So I already know the value of quality control sera. And if the value that I get from my experiment falls within the range, then I am sure that I have run the test perfectly. So if I have run the test correctly, then obviously the patient sample which I have also run, the value that I have got from that patient sample is also correct. So these are two basic reasons why we use quality control sera in our day-to-day life. Friends, when we talk about quality control sera, we interchangeably use three different terminologies. One is standard, one is calibrator, and one is control. But all these three different terminologies have three different meanings. We will try to understand one by one what is the meaning of standard, what is the meaning of calibrator, and what is the meaning of control, and how they are different from each other. Friends, when we talk about standard, so the standard is a liquid in which the value of analyte is fixed. It has one single constant value. And the standard is usually it is a synthetic material. It is prepared in a laboratory. Now, say for example, we want to estimate glucose and then we purchase the glucose kit from any manufacturer or a distributor. Now, when we open this kit, along with the reagent of glucose, we will also get the standard of glucose. So this standard of glucose is nothing but it is a synthetically prepared solution in which the value of glucose is already fixed. Say, for example, the value of glucose is 100 milligram per deciliter. So the value is fixed at 100 milligram per deciliter. This value of glucose will not change. Similarly, if we talk about calibrator, then calibrator is also a liquid in which the value of analyte is fixed. But usually calibrator is not synthetically prepared. It is a biological material. Now, what do I mean by biological material? Biological material means, say for example, I have taken 10 different serum samples. All these serum samples are from healthy patients, healthy people. And then I mix the serum of all these 10 people and I mix it in such a way that the serum is homogeneously mixed. And then when I calculate the value of glucose in that particular serum, and that value of glucose is fixed. Say, for example, the value of glucose is, for example, it is 115 mg per deciliter. Then that fixed value of glucose in the human serum sample is behaving like a calibrator. So calibrator is nothing but the value of analyte is fixed, but the material is not synthetic. It is a biological material. Similarly, if we talk about control, here the difference is that although control is a biological material just like calibrator, but here the value of any particular analyte is not fixed. Here the value is given in the form of a range. For example, if we talk about calibrator, then the value of glucose in the calibrator is 115 milligram per deciliter. But the range of glucose in the control will be, say for example, 100 milligram per deciliter to 130 milligram per deciliter. So this range of 100 to 130, this range is very, very important for control. So when we talk about control, then always the values will be between a range. And when we talk about calibrator, always the value will be fixed. It will not be in a range. It will be a fixed value. This is the difference between calibrator and control. Although both are biological material, but here the value is fixed and here in control the value is between a range. So whenever we use these terminologies in our day-to-day life, we have to be aware that what is the terminology that we are using. If the standard is given in the kit, we use the word standard. Sometimes the calibrator is given in the kit. The standard is not given in the kit. So in that case, we use the word calibrator, not the standard. And in most cases, controls are not given as a part of the kit. Sometimes the controls have to be procured from an external agency. So we need to understand these three different terminologies. Now, how many different types of controls are there? Friends, there are many different types of controls which are available in the market. The one that you see on the slide is only for an example. Sometimes the values which are given in the liquid which is there in the control is directly to be used in the pathology lab. This type of control is called as liquid stable control because here the liquid is ready to use. But sometimes when we see the control vial, there is no liquid in the control vial. There is a powder which is there in the control vial. Here we have to add water in the control and we have to convert this powder into a liquid before using it. Such type of controls are called as lyophilized. Sometimes what happens is when we take the control vial, we see that the values, the range of every particular analyte is already given in the value chart. This type of control is called as assayed control, where the range or the values of any particular analyte is pre-printed in the value chart. But sometimes, friends, what happens is the values are not printed in the value chart. The entire control is given without a value chart. Such type of controls are called as unassayed controls. Sometimes controls are only for a particular set of parameters that belong to a segment of clinical chemistry only. Such type of controls are called as clinical chemistry assayed controls. But sometimes the values of the analyte do not belong to the segment of clinical chemistry. They belong to the segment of hormones, for example. Then in that case, we will see that this control is called as hormone acid controls. So these are different types of controls which are available in the market. We have to understand this before using controls in our day-to-day life. So if I want to run a T3, T4, TSH test, and if I'm using a clinical chemistry control, I will not find the values of T3, T4 or TSH in a clinical chemistry control. I have to go for a different type of control. Sometimes want to run, say for example, lipid profile. Then in case of lipid profile, I cannot use a hormone control. I have to go for a clinical chemistry control. So we have to first decide that why we should use the control. And subsequently, we have to procure the type of control which is available in the market. What are the different types of characteristics for the controls? Every control vial has a certain set of characteristics. Like we already discussed before, for every analyte in the control, there is a range of that particular analyte, which is given in the value chart. Now, this range also has something called as a target value. We will understand in future what is the meaning of target value, what is the meaning of a range, how this target value and range are decided. We will understand that later. But in every control vial, for every parameter or every analyte, there is a target value and there is a range. The range is usually between plus and minus 2 standard deviation. In short form, it is called as plus minus 2SD. Now, again, we will understand in our future video lectures what is the meaning of standard deviation, what is the meaning of plus minus 2. We will all understand that in the future. For now, just try to understand that every parameter which is there in the control should have a target value, it should have a range, and the range should be plus minus 2 SD from the target value. The values of this control is specific to that particular lot number of the control. This is very important to understand, because if I have two different controls from the same manufacturer, the value of glucose in first lot number will be different from the values of glucose in second lot number. So if I am using the control of one particular lot number, whenever I change the next lot, I have to also look at the values of glucose in second lot number. I cannot refer to the value chart of the first lot number. Therefore, it is important to understand that values of every analyte is specific to that particular lot only. We also have to understand that if the controls are available in lyophilized form, that means if the controls are in powder form, and when we add distilled water into the powder and we convert this powder into a liquid, then every parameter or every analyte has a particular shelf life. Some parameters, whatever the range is mentioned in the value chart, that range is stable only for the first 48 hours after reconstitution. But for some analytes, the range is applicable for 30 days after reconstitution. So for different analytes, there is a different shelf life after the reconstitution. Moreover, the whole control vial itself has a shelf life after reconstitution. That means as long as the controls are in the powder form or in the lyophilized form, it has a shelf life of, let's say hypothetically, up to 2 years, which is printed on the label of the control vial. But when we add distilled water and we reconstitute this control, then the shelf life is not 2 years. Then the shelf life is reduced to only 30 days, as long as it is kept in minus 20 degrees. So all these characteristics we have to understand before using the controls. Same thing is also applicable for calibrator. The value of calibrator, the analyte in the calibrator is specific to that particular lot only, and the shelf life of the calibrator is reduced when the calibrator is converted from lyophilized into liquid form. Just the difference is that in calibrator the value is a constant value and in control it is a range. That's the only difference. Now, how do we really reconstitute the controls? We have seen that controls are available in lyophilized format. And once we add distilled water into the lyophilized powder, then the shelf life of this liquid is reduced. This step of adding distilled water and reconstituting the control vial is very, very critical. Because if we don't do it properly, then the concentration of the analytes will change. Say, for example, if the control vial has a reconstitution volume of 5 ml, and instead of adding 5 ml, if we add only 4 ml in the control vial, then the concentration of that particular analyte will increase and it will not be as which is printed in the value chart. So it is very critical to understand how do we reconstitute the control vials. So for reconstituting control vials, we need to first take distilled water and we need to add the volume of distilled water which is printed either in the pack insert of the control or on the label of the control vial. Let's say, for example, if we have to add 5 ml of distilled water in one vial of control, then we have to accurately take 5 ml only. And then we have to add in the control vial. And we have to mix control vial in the direction of number 8. This will ensure that the contents of the powder are equally distributed in distilled water. Sometimes the directions to mix and how much time we have to mix are printed on the pack insert or on the label. So if we have to add distilled water and if we have to wait for 30 minutes as per the instructions in the pack insert, then we have to follow that instruction very, very precisely. We cannot start using the control immediately after adding distilled water because the powder has not homogeneously mixed with water. So for that, it takes somewhere about 20 to 30 minutes. Now, once we have added 5 ml of distilled water and we have waited for 30 minutes, we have also mixed the contents in number 8 direction. After that, what we need to do is we need to take 50 microliter from that particular solution and we need to add that 50 microliter in a fresh and clean dry append-off tube. Similarly, we take another 50 ml into second append-off tube, so on and so forth. Like this, we get 100 different append-off tubes. All these 100 append-off tubes we need to keep at minus 20 degrees. The reason is because the reconstituted control vial is stable for 30 days if and only if it is stored at minus 20 degrees. So we reconstitute this in smaller volumes. This step is, in technical language, it is called as aliquoting. So we aliquot 50 microliters of this control in append-off tube and we freeze it at minus 20 degrees. Here we also write the date of reconstitution on the label of the append-off tube. Because from this date of reconstitution, for next 30 days only, this particular append-off tube has to be used. If we don't use it, we have to throw it away. Then we have to take one append-off tube at a time. Let's say I do this exercise on a Monday and I keep all the 100 Eppendorf tubes in -20 freezer on Monday. If I come to my lab on Tuesday, I will take only one Eppendorf tube. I will bring the liquid to room temperature first, and I will use this control in my day-to-day test. If there is any amount left, I have to throw it away. I cannot again keep it at -20. So this is a one-time use and throw control which I have prepared. So this activity of aliquoting is very, very important. Now, when I use this control in my day-to-day test and I get any value, I have to check that value whether it is in that particular range or not by referring to the value chart of that particular lot number which I have used, which I have now reconstituted. So this is the correct way of using the control. Now, how do you read the instructions for use for that particular control? There are certain tips to read the instructions for use. Number one tip is that the instructions for use has to be from the same batch number or same lot number, because we understood that once the lot number changes, the value of that particular analyte also changes. Therefore, we cannot see the value chart or instructions for use from some other lot number. Secondly, when we check the value chart or the instructions for use, there are different instruments that are mentioned in that particular value chart. So if I am using an instrument of a particular company, then I have to refer the value of that particular instrument only. Suppose, for example, I'm using a Beckman-Coulter instrument in my lab, and there is a value chart for Beckman-Coulter specifically. Then I have to refer to the value chart of Beckman-Coulter only. But if I'm using one particular instrument which is not mentioned in the value chart, then I have to look at something called as mean of all instruments. So whether do I have to look at the value chart of a particular analyzer or instrument, or do I have to look at mean of all instruments? This is very important because the value range of that particular analyte is different for different analyzers. Then the third thing that I have to follow is the methodology. Say, for example, I want to estimate glucose. Then if I follow GOD-POD method, the range will be different. If I follow hexokinase method, the range will be different. Similarly, if I have to estimate creatinine, if I follow IFCC method, the range will be different. If I follow enzymatic method, the range will be different. So I have to follow the method by which I have estimated either glucose or creatinine. And I have to follow the range of that particular method only. These are certain tips to use the instructions for use. We'll just give you one example of how an instructions for use looks like. This is how the IFU or the pack insert of a particular control looks like. Here, if you see, we have highlighted something called as lot number. This lot number is very, very critical. The lot number which is printed on the vial of our bottle has to match with the lot number of the value chart or the instructions for use. This is very critical. Then secondly, we have to look at something called as storage and stability. Here, there will be instructions given on how to reconstitute the control, how to store the control, what values, what parameters will get degraded first. All this information is given in this particular section. So if you just read with me what is written over here, it says that after reconstituting and storing tightly capped at 228 degree, this product will be stable as follows. All parameters or all analytes will be stable only for 7 days, except free T3, acid phosphatase total, and prostatic acid phosphatase, which will be stable only for 3 days. So friends, do you see that if I have to estimate, let's say free T3, then I have to use this control within the first 3 days if I'm storing at 228 degree after reconstitution. Because after 3 days, the value of free T3 will be not same as what is mentioned in the value chart. Similarly, after reconstitution and frozen, that means at -20, when reconstituted and stored tightly capped at -10 to -20, this product will be stable as follows. All the analytes will be stable for 30 days, except tobramycin, which is stable for only 20 days, free T3, which is stable for only 10 days. So if I have to estimate free T3 and I'm storing at -20, then I have to use this control within the first 10 days after reconstitution. I cannot use it after 10 days. Similarly, they have given the instructions that once thawed, that means thawing means bringing it to room temperature again. So once thawed, do not refreeze this product. Discard the remaining material. This product is shipped under refrigerated conditions. So they have very clearly mentioned that once you bring this control to room temperature, that means the aliquot to room temperature, then that particular aliquot cannot be again refreezed. If we are not able to consume it, the remaining volume we have to discard. So that is why this instructions for use is very, very important to understand. Now we also understood in our previous slide that controls have the particular range or fixed analytes for which the range is given. Now here we can see that in this particular control, these are the parameters for which the range is mentioned in the value chart. If we have to test for any parameter which is not in this list, then this control is not going to work for us. We have to use a different control. We saw in our previous slide that for every control, there is a fixed value of parameters that for which the value is given in the value chart. So in this particular control, the value chart has values for only these particular parameters. Now, a value chart looks something like this, which is on the right hand side. Say, for example, there is a parameter for, let's say, albumin, for example. Now, here in albumin, you see the unit is gram per deciliter, and there is something called as mean, and there is something called as range. This mean value is nothing but the target value of the control of that particular analyte. And this range is nothing but it is plus minus 2 SD value from that particular mean. How do we calculate it? We will see in our future videos. But the company has already calculated the mean and the company has already calculated plus minus 2 standard deviation. And they have printed this in the form of a value chart. So here, this is not for a particular analyzer. If these values were for a particular analyzer, then the name of that analyzer would also have been printed over here. But here the name of the analyzer is not printed. That means it is mean of all instruments. So here you can see that for many analytes, the mean and the range are mentioned in the table. This is called as value chart. Friends, I hope that you have now understood what exactly is control and what exactly is the use of the control in our day-to-day life. Now, we saw in our previous slide that while aliquoting, we reconstitute 5 ml and we distribute this 5 ml in 100 different Eppendorf tubes, small volumes of 50 microliter. Now, what I usually do as a laboratory owner is that whenever I come to the laboratory, I will take out one Eppendorf tube and I will run this Eppendorf tube along with all the tests that I do on that particular day. Say I am interested to understand the value of glucose only, just for example. So for glucose, I will take out the one particular Eppendorf tube and I will bring it to room temperature and I will run glucose from that particular aliquot. This I will do on day number 1 after reconstitution. So if I reconstituted on Monday, I will do this activity on Tuesday. Again, I will come on Wednesday. Again, I will bring one more aliquot to room temperature and I will do glucose estimation from that particular aliquot. Again, I will do the same activity on Thursday, again on Friday. So I will keep on doing this activity for one particular month. For 30 days, I am doing this activity. Now, whatever value of glucose I am getting, I will plot this value of glucose on a graph. So the graph will look something like this. So here, let's say this center line is the mean of glucose. Let's say the mean of this, just for you to understand, this is an example. If the mean of glucose is 252.3, then 1 SD is 262 plus that is plus 1 SD and plus 2 SD is 271.6. Minus 1 SD is 242.7 and minus 2 SD is 233. So the mean of glucose is 252.3 and plus minus 2 SD, the range is between 233 to 271.6. Now, when I did the glucose test on day number 1, this is the value that I got. Then I again I ran glucose for day number 2. This is the value that I got over here. Similarly, on day number 3, this is the value of glucose. Day number 4, this is the value of glucose. Day number 5, this is the value of glucose. So I will keep on checking the value of glucose every day. And I will see that whether my glucose values, the one that I am testing right now, whether these values are coming between plus minus 2 SD range or not. If the values are coming between plus minus 2 SD, then I am confident that all the tests that I have performed on that particular day are also correct. So if we plot this graph on month to month basis, this type of graph is called as Levey-Jennings curve, or this is also in simple language called as Levey-Jennings graph. So Levey-Jennings graph tells us information that if we reconstitute the control and we randomly use the control on that particular day, if the value of that particular analyte is in the range, that means all the patient values are also correct. Now say for example, in this control, the glucose value is in the range, but SGOT value is not in the range. Say for example, SGOT value has gone beyond plus 2 SD. Then can I depend on the results of SGOT of that particular day? Answer is no. I cannot depend upon the SGOT test that I have performed on that particular day. So something is wrong. I need to check what is wrong. So this is how controls are used in our day-to-day life. So Levey-Jennings curve will try to give us a pattern, or it will give us a trend that if on day number 1, the value of glucose is on the mean and every day the value of glucose is increasing only, then something is wrong. Every day the value of glucose is in the decreasing side, again there is something is wrong. So we can see this type of trend using this Levey-Jennings curve. Friends, I hope this video has been helpful for you. If you have any kind of questions, please write in the comment section, or please help us to improve our future videos by giving us any kind of suggestions that you have in your mind. Thank you very much. I will see you in the next video.